Imagine standing at the edge of a harbor, watching a massive steel ship glide across the water. Thousands of tons of metal, engines, cargo, fuel, machinery. It looks impossibly heavy. If you drop a small metal spoon into the sea, it sinks instantly. So why doesn't a ship made of the same material plunge straight to the bottom? The answer lies in one of the most elegant principles in physics: buoyancy. At first glance, it feels almost magical. A floating city made of steel resting calmly on water. But beneath the surface, invisible forces are at work. Forces that depend not on weight alone, but on density, pressure, and displaced water. To understand buoyancy, imagine lowering your hand slowly into a pool. As it goes deeper, you feel pressure against your skin. That pressure comes from the weight of the water above. The deeper you go, the greater the pressure. Now imagine an object submerged in water. The water pushes against it from all sides. But here's the crucial detail. The pressure at the bottom of the object is slightly greater than the pressure at the top, because pressure increases with depth. This difference in pressure creates a net upward force. That upward force is called the buoyant force. More than 2,000 years ago, the Greek scientist Archimedes discovered the rule governing this force. According to Archimedes' principle, an object submerged in a fluid experiences an upward buoyant force equal to the weight of the fluid it displaces. In simpler terms, water pushes up on an object with a force equal to the weight of the water the object pushes aside. This is the key to why ships float. When a ship is placed in water, it begins to sink slightly. As it sinks, it displaces water, meaning it pushes water out of the way. The more it sinks, the more water it displaces. As long as the weight of the displaced water increases, the upward buoyant force increases. Eventually, the buoyant force becomes equal to the weight of the ship. At that moment, the forces balance. The ship stops sinking. It floats. If the ship were heavier than the maximum buoyant force the water could provide, it would continue sinking. So why does a small spoon sink while a massive ship floats? The answer lies in density. Density is mass divided by volume. A solid steel spoon is compact. It has high density because a lot of mass is packed into a small volume. When you drop it into water, it displaces only a small amount of water, too little to generate enough buoyant force to balance its weight, so it sinks. A ship, however, is not a solid block of steel. It is mostly hollow. Inside is a vast volume of air. This increases the overall volume without greatly increasing mass. When you calculate the ship's average density, including the air inside, it becomes less than the density of water. Because its average density is lower than water's density, the ship can displace enough water to balance its weight before it sinks completely. In other words, ships float not because steel floats, but because the ship as a whole is less dense than water. This principle explains many everyday experiences. A person floats more easily in salt water than in fresh water because salt water is denser. Higher density means a stronger buoyant force for the same displaced volume. It also explains why submarines can dive and resurface. Submarines adjust their buoyancy by filling internal tanks with water or air. When tanks fill with water, the submarine's density increases and it sinks. When water is pumped out and replaced with air, density decreases and it rises. Even hot air balloons operate on a form of buoyancy. Instead of floating in water, they float in air. Heated air inside the balloon becomes less dense than the cooler surrounding air. The buoyant force from displaced air lifts the balloon upward. Buoyancy is not limited to liquids. It occurs in gases as well. The same physics applies. Stability is another important factor for ships. A ship must not only float, but remain upright. Engineers carefully design hull shapes so that the center of gravity remains below the center of buoyancy. If these are misaligned, the ship can tip. When cargo shifts unexpectedly, or if water floods part of the hull, the ship's center of gravity can change. If it rises too high, stability decreases and the vessel risks capsizing. The shape of the hull also matters. Wide hulls provide greater stability. The curved bottom allows smooth water displacement, reducing drag and improving efficiency. Even waves and storms demonstrate buoyancy in action. As waves pass beneath a floating object, the object rises and falls because the buoyant force changes slightly with water level. But as long as the average buoyant force balances the weight, the object remains afloat. There is something profoundly counterintuitive about buoyancy. We tend to think heavier objects sink and lighter objects float. But weight alone is not the deciding factor. It is the relationship between weight and displaced fluid. A massive cruise ship weighing hundreds of thousands of tons can float, while a tiny pebble sinks instantly. The ocean does not judge by size, but by density and displacement. Right now, if you are near water, imagine dropping different objects in. A wooden block floats because wood is less dense than water. A metal coin sinks because its density is higher. But reshape that metal into a hollow bowl and suddenly it floats. The material did not change, the density did. Buoyancy reveals an important truth about physics. Balance determines behavior. Forces do not act in isolation, they interact. When gravity pulls downward and buoyancy pushes upward with equal strength, equilibrium is achieved. Ships do not defy gravity, they work with it. Gravity pulls them downward, but water responds with an equal upward force determined by displaced volume. From ancient wooden boats to modern aircraft carriers, every floating vessel is a triumph of understanding this balance. The next time you watch a ship moving across the sea, remember that beneath its hull, billions of water molecules are pressing upward, supporting its weight with invisible precision. Floating is not magic, it is physics in perfect equilibrium.